All right, so here we are. Now, yesterday, of course, we wrapped up chapter 10, and we also actually made quite a bit of progress on the sample final. So let me go get that off of Moodle and we can carry on. Find that. And let's see. Yes, send me a push. All right. So I did post the actual chart test as well as not the test, the sample final, as along with the solutions that we just started. So today we'll pick it up from there. Basically, what we did was we went through the fill-ins, and then I gave you hints as to how to solve the rest of them. And there was the one, remember, number 7 that doesn't belong in there. So yeah, don't forget about that. So hold on one second. Oops. Okay, so today is the 12th. So we'll call this part 2. All right. So yeah, let's get back to where we were. Now, of course, remember, this is based on chapters 8, 9, and 10. So the questions could come from any of those 3. And so what I'll do is I'll build on yesterday's hints to go through and show you the exact, oh, by the way, of course, we need the tables. Hold on one second. Yes, because we may need both the normal tables and the t-table for these questions. So we've got normal 1, normal 2, and t. Okay. All right. So yes, I think I mentioned this once or twice. You can see the normal distribution shows up basically everywhere in statistics. If you took 10 more chapters, of course, with 10 more chapters, you'd probably use the normal distribution in every single one of them. Same thing with the t-table, the t-distribution rather. These are 2 of the most important distributions in all of statistics. And so understanding these is a huge deal because they show up almost everywhere. They're so important and so useful that we almost never stop using them, basically. So anyway, let's see, where did we leave off? By the way, I just want to point out that all the announcements contain all the information you need about when everything is due. So officially, as we discussed yesterday, the class actually officially closes on Monday, but we are actually going to be finished today because there's nothing left to do really except finish up the sample final. We actually finished early. I'm not surprised because it's been my experience with these online classes that somehow it just goes faster than in the classroom. I noticed that right away when in the spring of 2020, when we switched abruptly from classroom to online. I noticed it pretty quickly. There's just something about the online format. It just seems to go faster. And so we are done after today. And so from this point on, all you have to do is finish up all of your assignments, and the dates are all listed in here. And the absolute last day that anything can be handed in will be Tuesday, the 18th at midnight, because the grades are due a couple days after that. Let's see. Yes. That would mean the chapter 9 and 10 problem sets and the final. So in other words, by the time it gets to be Tuesday night at midnight, I would like to have absolutely everything in my possession so that we don't want any delays with the grades. We don't want to deal with incompletes. We just want to get it over with. Okay. So try to make sure everything's done by Tuesday at midnight. And in the meantime, of course, you can always reach out to me for possible Zoom sessions or email questions, especially if there's something in here that is not crystal clear what needs to be done. All right. So, all right. Anyway, let's get back to this. So the first problem here is a museum owns 150 sculptures. That would be our population. So you notice we labeled it capital N. And the mean in this population is 100,000. That's mu, the population mean. And the population standard deviation is 20,000. So a sample of 25 sculptures is chosen. And what is the probability that among those 25 sculptures, the average is greater than 110,000? So the mere fact that they're asking about the average means that this is chapter 8. Okay, in other words, we're going to calculate a probability not for X, but for X bar, the average in that sample of 25 sculptures. And so if you recall in chapter 8, we have to make a key decision here. Is this a large or a small sample? And you might also recall that the decision comes down to the relationship between the sample size and the population size. So a small sample all right, let's put it this way. For these problems, a small sample means that the sample size is less than or equal to 5% of the population size. So in other words, you could write it as N is less than or equal to 0.05 capital N, or you could write the ratio of these two is no more than 5%. Now here, in this example, or in this case, that ratio, 25 out of 150, that's a pretty large ratio. That's 16.7%. Which is well above 5%. Therefore, this is considered to be a large sample. Okay, so that tells me that I must make an adjustment when I calculate the standard error. So actually, before we even do that, let me just go back to the top here and remind you that the mean, well, actually, even before we review that, let me just remind you that X bar is a normal random variable, or at least it's being treated that way. With a mean written as mu X bar and standard deviation and I'm going to put in parentheses, the alternative name for this is the standard error sigma X bar. Okay, that's what we need to know to calculate our probabilities. And when it comes time to converting this into a standard normal form, this is the formula that we'll be using. And of course, the purpose of doing this is to make it possible to use the tables. And you can see it's exactly what we were doing in previous chapters. It's just that the calculations are a little different. In other words, it used to be, just a quick reminder, in chapter 7, we use this formula. So it's the same thing. You're just subtracting the mean and dividing by the standard deviation, but the definitions are a little different. Okay, now, another thing to note is that no matter what's going on, mean of X bar just equals the population mean. Okay? And this would be regardless of the sample size. That's not where we have to make a decision. The decision comes down here. So, so if we remember, for a small sample, means that this expression equals the population standard deviation divided by the square root of n, the sample size. And for our large sample, you have to make an adjustment to it. We need the so-called finite population correction factor. Okay, yes, so don't forget, as far as terminology goes, this is the finite population correction factor. So in this case, we're going to use the second version because we know that it's a large sample. It's quite large, as a matter of fact. All right, so let's start plugging in some numbers. So mu x bar equals mu, which you recall is from way back here, 100,000. In fact, let me split the screen so we don't have to scroll up and down 100 times. $100,000, and then the standard error so you'll have 20,000 of the square root of 25, and then here we'll have 150 minus 25 over 150 minus 1. Now that turns out to be approximately, you can round this to two places, I guess, 30, because it is dollars, 3663.72, approximately. Now, if you get a slightly different number, that's fine. The probabilities won't be affected that much, especially because when we use the tables, we're engaging in a fair amount of rounding anyway. If you need the exact, and I mean the exact values, then you need to use a software program like Excel. But for the most part, any inaccuracies that we introduce here will be very minimal by rounding. So we'll use 3663.72 as our standard error. So that means that whatever probability we're being asked to calculate, the conversion will be take whatever X bar you're looking for, subtract 100,000, and then divide by 3663.72. So the question is the probability that the average price is greater than 110,000. Okay, I guess we don't need this anymore. All right, so therefore, we take our 110,000, subtract 100,000, divide by 3663.72. And this is the same thing as saying, what is the probability that Z is greater than or equal to 2.73, let's say. And again, obviously that's an approximation, but that's close enough. And of course, as usual, when we're using tables, we have to round this to 2 decimal places. Yeah, it's 2.729 something. That's fine. Make it 2.73. Now, of course, this is a greater than or equal to probability, which means we can't look it up directly in the table. What we have to do is this. All right, so let's go to that table and find, now 2.73 is a very large number for the normal distribution. The table, if you've noticed, only goes up to about 3. So we're really getting to the bottom of the table here. Look at this. So here's 2.7. Now, I can't split the screen here, but this is the column for 0.03. So it's this number that we're looking for. In fact, you know what you could do. Write these down here. So yeah, it's 0.9968 that we're subtracting. So the final answer is 0.0032. So it's highly unlikely that the average for the entire group of sculptures is greater than 110,000. So now this might come in handy if we're trying to figure out how much insurance to buy, for example. You know, like when you buy insurance, you get a choice, especially for something like this. They'll ask you, what is the value of the property that you're insuring? And of course, insurance can be very expensive. So you don't want to overdo it, but you also want to have adequate coverage. So, and if you don't want to necessarily go through the entire collection and inventory it, you might use this as a first approximation. You can say, well, listen, if it's that unlikely that the value is above 110,000, why don't we insure the collection for 110,000 per piece? That should take care of it. Anything more than that would probably be overkill, but then anything less than that might not be enough. All right, so that's how that one works. Now, the next one is very similar because if you look at it carefully, you'll see once again, we're being asked to calculate a probability for the average right there, the mean number of pages. This involves ink cartridges where we're thinking about how many pages can they print. So we're given all the information. The population in this case is enormous. Okay, this company has made 1 million cartridges and they're going to take a sample of 40. So we don't even really have to calculate that ratio. It's pretty obvious that this is a small sample, but you can do it anyway if you want to. But it should be pretty clear this is a small sample. So what that means then is that these are the measures that we need for this problem. And that's about, let's round it to 7.91. So again, there's a fair amount of rounding there, but that will do the job. Okay. And now the problem that we're looking for is less than or equal to 390 pages. So this one is more straightforward. Because it's already less than or equal to Z. This is about 1.26 negative, sorry, negative 1.26. Okay. Now we can just go to the table, the negative table that is, and look this up directly. Let's go get the negative table, 126. There we go. And that gives us an answer of 1038. In other words, it's not likely that you get a cartridge. Let's say you're the customer and you buy 40 cartridges for your office. Okay, you got a lot of people working there and they need printers. You buy 40 cartridges and the chances of them printing less than 390 pages on average, that is very, very small. So you might say, well, that's fine then they're worth the money because I'm pretty confident I'll get a minimum of 390 pages out of each one. All right. If not, that means you're unlucky. All right. Or you got a bunch of duds or something. And they'll probably have to give you your money back. All right, now look at this one. Now, this is the first one that explicitly mentions the words confidence interval. So there's no doubt in our minds what we're trying to do here. We're constructing a confidence interval, specifically a 99% confidence interval. But here we have to make a decision. Do we use the t distribution or the standard normal or z distribution? Okay, so remember the rule is that use t when sigma, this population standard deviation, sigma is unknown. In other words, the sample standard deviation is given in the problem. So in other words, the problem itself may not say the actual words, the population standard deviation is unknown. But if they give you the sample standard deviation, that implies that we're using that instead of the population standard deviation. Okay, so just the mere fact that it says the sample standard deviation is X, that's enough to know that we're using the t distribution. On the other hand, use z when the population standard deviation is known and it's given to you in the problem, then you know to use it, okay? So in other words, it comes down to really which one is given to you in the problem. Right? There's no attempt to be tricky. Let's put it that way. They won't say, for example, well, you know, here they are. There's both of them. No, the one that you're given is the one that you'll use. Okay, so here, for example, it says the words, the sample standard deviation is 842. Nowhere in here does it say that we don't know the population standard deviation, but that is implied by the fact that they gave us the sample standard deviation. So once you see those magic words, sample standard deviation, automatically you use t. If they tell you it's the population standard deviation, automatically you use z. End of story. Okay, now of course, now that we know that it's t, we have to remember to look for or calculate the degrees of freedom because we need that for the table. All right, so what are we trying to do? Confidence interval for the population mean. By the way, one more thing. Remember, that's one more important detail. We might be asked to do this for the population proportion. Make sure you know which one it is. And also, the formula for this would therefore be, since sigma is unknown, the confidence interval takes the form it's always x bar plus or minus something. Here that something is t s over radical n. And remember, this second part is our margin of error. That reflects how much uncertainty there is associated with each sample mean. Because you know that when you take samples, they don't necessarily perfectly reflect the underlying population. On average, they should, but some can be different, very different. So that's what this is all about. Now, the first thing we should always do is look up the t value in the table. Then the rest is easy, just plug it in. Now, remember, we did say it's a 99% confidence interval. And it says, you can see right here, that means alpha is 0.01, but it also means that alpha over 2 is 0.005. Now, luckily, though, this table actually has at the bottom, and they don't all have this feature, it actually labels for you the confidence levels for each one of these columns. In some books, it doesn't appear down there, and so you have to figure it out yourself. I like this setup. In other words, all you have to do is say, oh, here it is. It's 99%. But now, how many degrees of freedom do we have? Oh, well, that's easy. It's just n minus 1. Now, the sample size is 10. Therefore, we have 9 degrees of freedom. And so we'll scroll up here in this column. You just barely see it. 3.25 is the appropriate t-value or t-score. Then we have that information in hand. We can plug in everything else very quickly and easily. So first, let me split the screen. And so we have on the X bar was 2427 plus and minus 3.250 times 842 over the square root of 10. So when you do the calculations, let's see. Let's try that. 842 divided by the square root of 10 times 3.25 is approximately equal to, this is also dollars. We can round it to two places, 865.36, let's say. All right, so now, oh, whoops. Let's do that. All right, so basically remember, what are we actually doing here? We've got 2427 minus 865.36, comma, 2427 plus 865.36. All right, so let's do that. 2427 minus 865.36. 1561.64 is the lower limit of this interval, and the upper limit is 3292.36. Okay, so think of this as the lower limit, and this is the upper limit. So basically, we're 99% confident that the average customer is spending this much on their vacation, somewhere in that interval. The population mean is highly likely to be contained in that interval. So this is how they decide. Oh, sorry, somebody's chatting. I didn't see that. Oh God, did I not post that? Oh my God. Oh, I'm so sorry. If that's the case, ooh, that was bad. Is it really not there? Jesus. All right, I apologize, everyone. It looks like I somehow forgot to post the thing. All right, I'm glad you pointed that out to me. It would have been kind of awkward for you to do your assignments without it. Yeah, let me get it in there then. Okay, well, it's down here in the bottom now. I mean, it should be up here with the normal tables, but yeah, I should have posted it in the same day I posted chapter 9, but here it is. Okay, so when you open it up, just be aware that for confidence intervals, you can look in the bottom. The top is meant for hypothesis testing when you only have either the right or the left tail, although you can use it for all three cases. So the top is really meant for hypothesis testing. For confidence intervals, you want to use the bottom because everything's spelled out for you right there. All right. So, all right, now that disaster is resolved. And yes, I want everyone to have the same tail. I mean, you could have looked it up on Google, but then they may all be slightly different. I would prefer that everyone have the same table available to them because, like I said, look how nicely this is set up down here. By the way, I just wanted to point out, I didn't point this out before. If you notice on the left-hand side, the degrees of freedom are increasing as we go down. What they've done here is they filled in the z-scores for those confidence levels. Why did they do that? Because what they're trying to tell you is that as the degrees of freedom keeps increasing, look how close these numbers are getting to the z-score. So at some point, when the sample size is large enough, you can feel free to just go ahead and use the z-scores. Now, we don't have any examples like that, but if you really had an enormous sample, at some point, it no longer matters if you're using the t or the z. But for our cases, just continue to use the t when s is given to you. All right. All right. Okay, so that one's done. Now here's one. Now this explicitly tells us that it's a hypothesis test. So for the most part, these questions, it should be pretty clear, since realistically, we only had 3 basic types of questions in these last 3 chapters. Questions about X bar, which are typically probabilities. And then we had confidence intervals in chapter 9. And then we had a hypothesis test in chapter 10. It should be very clear from the question what you're supposed to do. All right. So like here, it specifically says the words, test this hypothesis. What we're trying to find out is whether or not the mean GPA is greater than 3.2. So the null is always written this way. The mean equals that number. The alternative is this one. We're looking for evidence that the mean is above 3.2. Let's just say that this school is hoping to see a very high GPA. Let's just say that they want to move into the big time, like they want to be, they're trying to basically expand into a new market. They're trying to promote themselves to a wider range of students. And in order to do that, they want to prove that their GPAs are pretty high, meaning that they have very, very good students going there. And they want to be able to brag that they have a GPA more than 3.2, but only if there's enough evidence to prove it. So we pick a sample of 100 students, and we're told that the sample mean is 3.28. The sample standard deviation is 0.20. And once again, just like with chapter 9, the rule is that use the t-distribution when the population standard deviation is not known. And use the z or standard normal distribution when the population standard deviation is known. So here, the mere fact that they told us that the sample standard deviation is 0.2 tells us that we should use the t-distribution. Okay, now here's what you need to do. Now this, of course, is a complicated process, but we've already got some of it done, right? You see what I mean? These first 3 steps are already essentially taken care of. And it tells you in there to test at the 5% level of significance, which is the same thing as saying that alpha is 0.05. Now, what about the test statistic? Remember, there's only 2 possibilities here. The form is the same in both cases, but since we know that we're using the t-distribution, that indicates that we should use S here instead of sigma. And we are following the t-distribution. So this equals 3.28 minus the hypothesized value. This is mu0. What we think it is. This is our assumption. Until we see evidence that suggests otherwise, that's what we're going to assume. Now, what about the denominator? We need S. S is 0.20. And then this N is 100. And so when you plug in all those numbers, let's see what we get. Oh my God, that was interesting. It's exactly 4. Well, that doesn't happen very often. Well, what? Yeah, it's precisely 4. All right, now, what comes next, of course, is the critical value. Now, this is a right-tailed test. Okay, so remember how this works. Since it's a right-tailed test, how do you know that, by the way? Because the alternative is that the mean is greater than 3.2. A left-tailed test means it's less than, and a two-tailed test means it's unequal to. So the critical value is based on the alternative hypothesis. And since alpha is 0.05, the entire area in this tail is 0.05. This is my rejection region. The question is, what value of t represents the borderline between the upper 5% tail and the rest? So for that, we go to the table. And by the way, don't forget, now here the sample is oh, okay. See, now we're going to have a problem here. I just thought of it now. The problem is that the table doesn't actually have a row for 99. Oh, okay. All right. So, all right. So here's what we have to do. So first of all, the tail area is 5%. So go to the top, look for one tail 5%, and then scroll down. Normally you would look for 99 degrees of freedom. The table doesn't have it. So we're going to use 100 instead. Okay. The actual value will be so close. In fact, I'll tell you what I'm going to do. I have on one of my other calculators, I can look up for you the exact value for 99. And when I tell it to you, you'll realize that it's so close that this is fine. Hold on 1 second. I'm going to look it up real fast. Okay, you know what? Here's how close it is. With 99 degrees of freedom, instead of what you see there, it's 1.6604. So that tells me that we don't have to worry about it. So go ahead and use the 100, even though it's technically 99. The difference is so trivial that we don't really have to concern ourselves with it. That's one of the unfortunate things about these t-tables, though. The problem is that there's only so much room there. And so there's a tendency, once you get past, let's say 30 or 40, they tend to do this. But here's why. Once again, because when you get past 30, it's not that important to distinguish between the t and the z distribution anyway. So that's why the tables, there's no point in having, 99 and 98, 97, because they're so close to each other. So we'll use 1.66. And that's our t. So that's our critical value. So what actually just happened here is this. The critical value is 1.66. This shaded region is our rejection region. Our test statistic is way, way out here. So basically, remember the way this works is that since the test statistic is in the rejection region, we reject the null hypothesis and accept the alternative. Okay. Hypothesis, that is. All right, so in other words, we reject and accept and so now if the school wants to promote itself as having like really high GPAs, they can legally, well, they can claim correctly that their mean GPA is above 3.2. Maybe it gives them bragging rights, who knows, but they now have hard evidence that the mean is above 3.2 without having to actually check every single GPA. They have enough evidence to suggest that the mean is actually higher than 3.2. All right. What about this one? Now, this is another hypothesis test. We have a small company that wants to determine if the average salary is less than 100,000. A sample of 10 employees is chosen. We have a sample mean of 99,200, and the sample standard deviation is 1,200, which means we use the t-distribution. We're going to test the hypothesis at the 5% level. Now, if you notice, we're trying to find evidence that the mean is below. Let's just say they've decided that if the mean is less than 100,000, everybody gets a raise. Okay, they're feeling happy. The company's doing well. They may think that based on the industry standard, everyone in this company should make an average of 100,000. If it's not that quite there, they'll give everybody a raise. They're nice guys. How about that? It's a left tail test. Otherwise, they won't. I mean, if they don't reject this null, they'll just keep the salaries where they are. It's only if they reject the null that they'll give out the raises, because then they have proof, or I shouldn't say proof, hard evidence that the mean is lower than 100,000. All right, now because we're using the t-distribution, the test statistic is once again equal to this form. Now remember that this form never changes. If it was Z, we would just use sigma instead of S, but it's the same logic. So the mean is 99,200. The hypothesized value is 100,000. Okay, in other words, this number right here is mu0. S is 1,200. Square root of 10 is here. This is approximately equal to negative 2.108, or you can round it to negative 2.11. That's a fairly large number. When you see a number that large in the t-distribution, there's a pretty high chance that we're going to reject this null. But of course, we have to go through the formality of proving it. So let's do that. And how do we do that? By looking up the critical value. Now, since this is a left-tailed test, of course, it'll look like this. And everything below that is our rejection region. So let's go look in the table now. Oh, by the way, did we mention alpha? Alpha is, there it is. All right, very good. So that means in this case, the entire left tail has an area of 0.05. Oh, I'm sorry. You know what? I just realized this is not correct. This should say alpha, not alpha over 2. This is a left tail. My mistake. Alpha is 0.05. The entire left tail has an area of 0.05. Okay, so that's just plain alpha. When you go to the table, the sample size was 10, so we have 9 degrees of freedom. We have 5% in the tail. And let's go to the table now. Okay, let's go get it. And let's erase all this old stuff. So go to the top and look for 5%. One tail, 5%. And 9 degrees of freedom brings us to 1.833. But remember, it's negative because we're looking at the left tail. Right. So it's a left tail test. This table, by the way, will not have any negatives in it. It doesn't need them because it's understood that the symmetry will tell us what number we need if it's negative. Okay. So we have negative 1.833. So now we can draw our diagram. So this is our critical value, of course. But the test statistic, remember, was negative 2.108. So that puts it safely within the rejection region. So that means since, as always, since the test statistic is in the rejection region, we reject the null and accept the alternative hypothesis. So in this case, the null was that the mean was 100. Here we go. The mean is 100. The alternative was less. So you know what that means. This means that the company, if the company, now it didn't explicitly say this in the problem. If you notice, it just wants, you're just being asked to accept or reject the null hypothesis. But if the company was planning on giving a raise, I'm just throwing this in here. This was actually not part of the problem, but you see, the reason why I'm mentioning this is because some decision is going to be made based on this result. So let's say, as an example, if the company was planning on giving a raise, if the mean salary turned out to be less than $100,000, they now have enough evidence to suggest that a raise should be paid. Okay, so that's all they need to see. That's enough. They can say, all right, we don't have to test every single or check every single salary. We have enough proof to show that the mean is below 100,000. Therefore, we're going to raise the salaries. Okay, so notice if it's now if we were unable to reject the null, then they would have, I'll put that in parentheses, if the null had not been rejected, then no raises would have been given out. Okay, so that's how it works. But if you notice, it's a very conservative test because it's hard to prove, it's hard to reject the null. So that when it is rejected, that means we are quite sure that we've done the right thing. Okay, that's why it's set up this way. So this way, they're not going to just hand out a bunch of raises unless there's a clear need for it. Okay, now here's another, this is a confidence interval. We're back to confidence intervals, but this time we're dealing with proportions. How do you know that? A meteorologist wants to construct a confidence interval for the proportion of days, well, there you go, that it rains in New York State. Let's say we have a sample of 50 days, and during those 50 days, it rained on 7 of those days. Construct a 95% confidence interval. Now, the way proportions work is that we have X that represents the number of times a specific characteristic happened or took place. Here, that would be raining. So the sample proportion is 7 out of 50 or 14%. Also, because it's a 95% confidence interval, one minus alpha times 100 is 95%. That implies that alpha is 0.05. Okay. Now, here's a key detail. Always use the standard normal distribution for proportions, whether it's a confidence interval or a hypothesis test. And furthermore, the format, this confidence interval, is right here. Okay. So P, of course, is the sample proportion. And N is the sample size, as it always is. And then, of course, Z is the Z-score. Now, you might remember we had a chart somewhere along the way. I'm just filling it back in for you. So when we're using the standard normal, you really don't even have to look these up in the table anymore. You can just use them from this chart, or it's in the slides as well. So that means here it'll be simple. Remember, P is 0.14, and N, the sample size was 50. And since this is a 95% confidence interval, we'll use this one. You don't really need the plus and minus there because, you know, it's understood that with a confidence interval, you're going to both add and subtract, but we can leave it like that. Okay, great. So we've got 0.14 plus and minus 1.96 square root of 0.14, 0.86, 50, oops, And don't forget, this is our margin of error. Just in case the question asks, they may say, well, construct the confidence interval. And by the way, what is the margin of error? If that happens, then of course, it's the right-hand side. That's not impossible. It's possible the question may actually do that. It'll say, what's the confidence interval and what's the margin of error? All right, and then when you add and subtract, we're going to get approximately 0.0444 and 0.236. And of course, this is the lower limit of our interval. And this is the upper limit. So we're basically saying that the sample proportion is 14%, but we're 95% sure that the true value is between 4.4% and 23.6%. Of the, days raining in New York. Now, the thing about weather is that it's very tricky. It's unpredictable. So you can see that's why the range is so wide. Some years it gets into streaks where it rains all the time, and you get other years where it hardly ever rains. So it's not surprising that this has such a wide range of possibilities. One year it might be 4.4%. Another year it might be 23.6. You never know with the weather. It's just, it has a mind of its own. All right. So now remember, 7 doesn't belong in there. 8. Now this is a hypothesis test about the proportions. And remember, we did say that you must always use the Z, or standard normal distribution, with proportions. Okay, so always use the standard normal distribution with proportions. Okay, that's a little rule of thumb. Now, in this case, they want to know if the proportion of defective parts is more than 2%, because that is a problem. If that happens, we have to fix the way we're manufacturing this product. It's too much. Okay, it means the quality is not what it should be. So we take a sample of 150 parts, 4 are defective, which is 2.67%. So far we're kind of nervous. It looks bad. But we have to prove whether or not that's enough evidence to suggest that we should change the way we manufacture these parts. So, okay, hold on one second. So what we need to do is first come up with our test statistic. This can be written a couple of different ways. In the slides, it's written like this. There's a separate formula for sigma p. You don't even have to do it this way. The other option is to simply say, just write it out directly. Whatever's easier. Now, keep in mind, to be consistent with the previous hypothesis test, this is the hypothesized proportion. Remember, we're using pi for proportions in this book. And so that would be this thing. That's what we think is true. The actual sample proportion, though, was 0.0267. So you got pi 0, 1 minus pi 0, and the sample size was 150. Okay. So when all the dust settles, and by the way, I have separately calculated these two. This one turned out to be approximately 0.0114. So And then when you go through all the steps, Z is approximately equal to 0.588. Aha, now that is not a very large number for the standard normal. It doesn't look like we're going to be able to reject this null, because normally you got to figure at least 1.645 or more would be enough, but here it's not that big. So the critical value, now here's where we got to watch it. This is not a confidence interval. This is a right-tailed test. So that chart I showed you before is no longer valid. That chart is only for confidence intervals. What are we going to do instead? How do I know? Now, what exactly am I looking for? This is Z value, this Z score is the boundary. You could think of it as between the bottom 95% of this distribution and the upper 5%. So here's what we're going to do. We're going to go into the table and look for 0.95. Okay, so let's go look at this positive table. And when we're looking for 0.95, and this is the one that's not exactly there. It's halfway between two other values. This is kind of a nuisance, but here it is. It's halfway between 1.64 and 1.65. Okay, we've seen this one before. So we're going to call it 1.645. Okay. In other words, what this is saying to us is that the probability that Z is less than or equal to 1.645 is 95%. So that's why this represents the Z score that we need, because everything above that would therefore be 5%. This implies that the probability that Z is greater than this value is 0.05, and that's what we're aiming for. Now, by the way, if this had been a left-tailed test, then you would have had the critical value would have been negative Z alpha is negative 1.645. Now, if this had been a two-tailed test, we can use the chart or confidence intervals. All right, because then in effect, you're creating a 95% confidence interval. So let's go back to that chart, this one, and 95% corresponds to plus and minus 1.96. So therefore, what you would have seen is that just like with a confidence interval, the 5% is split up between the two tails. And therefore we have plus or minus 1.96, because this is equivalent to setting up a confidence interval for 95%. Now, if you don't remember that, what you could do, or look for 0.025 in the body of the table for negative Z alpha over 2. Okay, so let's do that. We'll go to the negative table. 0.025 is right there. Negative 1.96, which implies that positive Z alpha over 2 is positive 1.96. Okay, so the two-tailed test, like I said, is essentially equivalent to doing a confidence interval. So you can use that chart from up here. But for the others, you'll have to look that up in the table. All right. Now here, so getting back to this one, this is the right tail test. So here's what we have. So our test statistic, though, was only 0. Yeah, it's way over here somewhere. So it's pretty small. So therefore, what that means is that we do not reject the null that the proportion equals 0.02, which is good news because this means that the company does not have to change the manufacturing process, which is a relief to them. Okay, so one more thing, let me just sneak in one more detail here. Since the test statistic is not in the rejection region, do not reject. And therefore we don't have to change the process. Because even though the sample proportion was a little high, that it wasn't high enough to conclude that the entire population is above 2%. Okay. It just means we happen to grab an unusually tough, difficult sample, one that had more defects than usual. All right, so you know what? That was the whole thing. So we're done. So pretty much the exam itself, which I'll post as soon as we're done, basically. I just want to look at it, make sure I didn't slip in anything that doesn't belong, but I'll be posting it when we're done. And then, like I said, you should be able to do it by the 18th without any problems. It's exactly what you're seeing here. There's nothing in there that's the least bit meant to be, there's nothing in there that's meant to be tricky. Let's put it that way. It should be the same. Still, if something is wrong or it appears to be wrong, if you think something's missing, or if you're not clear about something, you can send me an email. And of course, I'll clarify it for you. It's not meant to be a tricky question, tricky test. I just want to make sure you can do these problems, and then that's all we can ask, that you know the material. Sometimes you get classes where the teacher tries to trick you, which I think is ridiculous. I just want to know if you know the material, and that's it. So it will be exactly like this. There's nothing, I don't think so. The only thing I can think of is this sample test did not have a question about sample sizes, though. Let me just go back to that for a second. Remember at the end, we had this discussion about sample sizes. And I just realized there are no questions on the sample exam about sample sizes. Remember, yeah, here it is. If we want to know how large our sample needs to be to keep our margin of error at a certain level or below, these are the formulas. They're very straightforward. But I don't remember if we have any of these in the actual exam. If there are, you can find the formulas right here at the end of chapter 9. Okay. And everything you need to know is right here. So, all right, other than that, I mean, no, it should be exactly the same. Yep, it's all here. All right, and also, as usual, I forgot to mention it today, if you are using the Texas Instruments 83 or 84 calculator, there's a lot of extra steps listed in here that you can use to come up with the same results. If you have that calculator, you don't actually need the tables because everything is built into it. But of course, you have to know how to use it. So I've included that here if you happen to be using those calculators. If not, well, that's fine. You'll just do exactly what we've been doing. But if you do, if you notice periodically, I've sneaked in these instructions so you can take advantage of that calculator. Okay. All right. So I guess instead of having a break, I guess we will conclude for the day because we're done. And I'll post the answers here. I'll post the test. And I guess that's it. It's went by kind of fast, didn't it? It's hard to believe that this has been going on for a month now, but it's true. And in 4 short weeks, you've learned as much as you would have learned in 16 weeks during the school year. And now, I guess your spring schedule can be a little lighter because of this. You've got a very difficult course out of the way in just a few weeks. And so you certainly have put your time to good use during this break, that's for sure. So great. Not only that, but when you get to your more advanced business classes, knowledge of this material is going to be very, very helpful, especially if you're studying either economics or finance. That's when they really come in handy. And some of the other classes too, but especially those two, because they're heavily based on this stuff. All right, well, if there's no last minute questions, I just want to say it's been a great semester, I hope. It has been for me. I hope you had a good time and you've learned a lot. And well, you never know. I mean, if you're at Purchase, the thing about Purchase, I typically only teach math for contemporary life and pre-calculus. But yeah, pre-calculus might be on your radar if you're thinking about taking more math courses. You should already be eligible for that. And it's, it does overlap with this a little bit, but we also cover a lot of other important topics. And you would need that if you're going to go on to Calculus 1 or 2, of course. So other than that, I guess I'll say goodbye to everyone, unless, like I said, if you have any more questions, you can send me emails and I'll try to get to them as soon as possible. All right. So I guess that will be it. Well, look at all this extra time you're getting. Use it wisely. Don't waste it. Okay. All right. Oh, here's a chat. Yes, you're welcome. All right. Is everybody else okay?
Thank you.
All right. You're welcome.